So good afternoon. My name is Dr. Richardson. The title of this course is An Introduction to Linear Algebra Using Python. My email address is srichards22@comcast.net, and you can use it to contact me anytime you have any questions on the lectures or problem sets or problem set solutions. Organizationally, please remember in this course that learning is not a passive activity. So take notes yourself, whether you're watching the lectures in real time or video clips of them. Problem sets are essential. You'll get nothing out of this course unless you do the problem sets. Problem set, the solution key to problem set 10 is available at the appropriate site on the website. And problem set 11 will be posted later on this evening. Again, you're encouraged to ask questions. And I suggest using a ruler in doing the problems and also in taking notes. You may find that to be very useful, very helpful. Okay, so last time we talked about the eigenvalue problem, and we looked at an example. So what I'd like to do today is look at an application of the eigenvalue problem. See how linear algebra helps us in this particular example. And this is an example from physics, which you may or may not have seen so far in your courses, but we'll review all the relevant background material so you'll be able to understand what's going on. So this problem is known as the coupled harmonic oscillator problem. And we are going to discuss it in some detail in lecture, and the rest of it will be outlined for you to solve in problem set 11. So the first thing we need to do before we tackle the coupled harmonic oscillator problem is have a review of elementary mechanics. So in particular, consider a floor on top of which there is a block. And this block has mass m. Now, there is a force on the block, which we'll call N, and N stands for normal, or perpendicular. So it's a normal force, which is the force on the block due to the table on which the block sits. So there's the table. It's probably useful to put a coordinate system in here. There is another force on this block due to gravity, call it W. And it's proportional to the mass of the block, and the proportionality constant is the gravitational constant of the Earth. So this force is the force on the block by gravity. So the central question you always ask yourself in mechanics is what forces act on a system? And in this case, the system is my block. And once you identify those forces, then you need to evaluate them. So what do I mean? Well, in this particular problem, again, I'm going to rewrite this diagram. So I'm going to replace the block by just a point. So there's a force F sub 1 and there's a force F sub 2. that both go in the plus and minus j hat directions, respectively. So you can add these two forces together, and according to Newton's second equation of motion, they will give you a acceleration, which is proportional to the mass of the object. So this is a vector equation. Now there are no forces. There are no there are no horizontal forces, sorry. There are no horizontal forces in this problem. There are no forces in the plus or minus j hat direction. There only are vertical forces. So you can resolve this vector equation into its components in the vertical direction, but this mass is at rest. Okay, it's not moving. So there is no acceleration. In the j hat direction. The mass is at rest. So in fact, we know what these forces are. F sub 1 is n, and F sub 2 is m times g. And so what we find out for this problem, and there's no reason to give this a subscript. So what we find out for this problem is that the normal force equals the mass times g, constant due to the gravitational field of the Earth. So this normal force, this guy here, is critical to the problem because this is the force that the table exerts on the block, and this force prevents the block from falling through the table. So if you just got rid of the table, then in fact, this object would just start falling due to the gravitational field. Okay, so vectors are important. Newton's equation, second equation of motion. That's also important. And again, you know, in some ways this is a review, but it's a useful review of some physics. So let's look at another example. Get more comfortable with how mechanics works. Here I'm going to have not one block, but two. So I have a block of mass A and a block of mass B. And again, they lie on the table. So the key question is, what are the forces acting on our masses? And this problem is slightly more complicated because now I have two masses, m sub A and m sub B. So I want to again use that same trick. I want to essentially represent mass sub A as a point particle. And so there's a force, and again, I'll use coordinate systems that look like this. So there's a force, F sub 1, And it is the force on mass sub A due to mass sub B. And similarly, there's a force which we'll call W sub A, and it's just the force due to gravity on mass sub A. Now, mass sub B, it's a little bit more interesting. There's a few more things happening here. First of all, mass sub B, just like the previous problem, has a normal force on it. So this is the force on mass sub B due to the table. There's a force which we'll call F sub 2. And what she is the force on M sub B due to M sub A. And if you think about it, there's a third force you have to pay attention to in this problem. That is W sub B, and that's the force acting on M sub B due to gravity. So we have two equations of motion to worry about in this problem because we have two masses. So let's tackle them one at a time. So for M sub A, I can write down that the vector force F sub 1 plus W sub A equals M sub A times the acceleration of that mass. Note that there are no forces in the horizontal direction. So this is exactly like the previous case. And even though there are forces in the vertical direction, there's no motion in this case in the vertical direction. So if you resolve this vector equation into its components, you simply get F sub 1 minus M sub A G equals 0. Now, let's focus our attention on M sub B. Well, that is this system here. So there are three forces acting on it. There's a normal force. It's a force F sub 2. There's a force due to gravity, W sub B. Again, this equals the mass times an acceleration. But again, the mass is at rest. So it's trivial to decompose this vector equation in terms of its horizontal components because there are no forces. Not pushing or pulling this system along the table. And you only have forces in the vertical direction, and you can write them in component form. And here they are. And again, there's no motion in the vertical direction, so they have to be equal to 0. So in summary, I have two equations. That's the first equation. And the second equation I have is this. Here are my two equations. And I like to combine them to see what they're telling me. Well, in order to do that, I need to exploit Newton's third equation of motion in this problem. And Newton's third equation of motion in this problem simply says that F sub 1 equals minus F sub 2. F sub 1 is the force on M sub A due to M sub B, and it is minus the force on M sub B due to M sub A. So I can write this as a vector equation where, strictly speaking, it's a zero vector on the right-hand side. I go back and look at F sub 1, the magnitude of F sub 1 and F sub 2. Note F sub 1 goes in the positive j hat direction. F sub 2 goes in the negative j hat direction. So now this is a zero on the right-hand side. And Newton's third equation of motion tells me that the magnitude of F sub 1 has to equal the magnitude of F sub 2. So I can take this equation, combine it with that equation, and that'll tell me that N equals F sub 2 plus M sub B G, and that equals M sub A G plus M sub B G, or that the normal force in the system is just the sum of these two terms. Now, does this make sense? Yes, because what this is telling you is that, let's go back to our problem here, that the table has to exert a normal force so this is the normal force which the table exerts, but it has to exert it on two masses. So it's different from the previous case. It has to exert it on mass M sub A and M sub B. Okay. Okay, so armed with this information, we can tackle a problem from elementary physics known as the simple harmonic oscillator. So the simple harmonic oscillator is an idealized problem. Namely, you have a wall. Attached to that, you have a spring and a mass. And in this particular case, the system is in equilibrium or is at rest. It's not moving. Now, a lot of approximations we have to make here. Excuse me, unlike the previous examples, we're going to ignore gravity. We are also going to make our lives a little more tractable by ignoring the mass of the spring. Now, this block, if you will have a mass m, and this spring can be stretched or compressed. And how easy or how hard it is to do that is going to be characterized by something called a spring constant K. Excuse me. And one more simplification to this problem. we are only going to look at one-dimensional motion. So you're not going to come along and bend the spring. You can either stretch it or compress it in the plus I hat or minus I hat direction. So let us look at this system now, which originally is at rest or in equilibrium. And now let's stretch the spring by a displacement, which will, by displacement of the mass, m, and this displacement of the mass we'll call u. So, as advertised before, rulers are your friends. So I have a new problem here. Originally, my mass was at a certain distance from the wall, characterized by that squeaky dotted line, and that was an equilibrium of the system. Here, what I'm doing is moving the mass to the right by some distance u. In other words, I'm stretching the spring. Well, you can build this system, you know exactly what's going to happen. You are going to feel a force, a restoring force on the mass due to the spring. Again, let's go back and recognize that my spring has a spring constant K, and the mass of the block is M. And this restoring force on the mass, M, due to the spring, is going to be in the minus I hat direction. So you pull this out, plus I hat direction, the spring is going to want to restore the system or pull it in the minus I hat direction. And this comes from reality. These are experiments that you can actually do. Now, if you come along, I mean, you can do this experiment provided you can make these approximations work. You may have to play with these a bit. Now consider the case where you compress the spring and the displacement of the mass but now you're displacing it by a factor u that is negative with respect to the equilibrium position. So let's draw a picture of what's going on here. There's my wall. I probably should put my equilibrium position in first. A dotted line. And now what I've done is compress the spring. So in fact, U is negative. So what happens here? Well, the mass is going to feel, again, a restoring force. So there's a restoring force on the mass due to the spring. So you always have to ask yourself, what's causing the force? And it's the spring. But this restoring force is now in the positive I-hat direction. Sorry, a little sloppy here. So you can put all this together. And write it in the form of a nice simple equation. This restoring force, F, in this system, this simple harmonic oscillator, is going to be proportional to the displacement of the mass from its equilibrium position the proportionality constant is going to be K. That tells you something about how easy or hard it is to stretch or compress the spring. And that restoring force is always going to fight you. So you need this minus sign. This is what the experiment tells you. So this observation was made by Robert Hooke several centuries ago. And this is known as Hooke's law. Okay. Now, what I like to do is look at this problem. So let us revisit this problem. With a little bit more detail. And this detail is going to serve us very well when we start looking at the coupled harmonic oscillator problem. So again, our physical system, our wall. Here's our spring, only motion in one dimension. Here's our mass. And in this particular diagram, I'm going to note the equilibrium position of the mass, and I'm going to call it L naught. I have moved the mass to the right by displacement, which I'll call U, and the distance from the wall to where the mass is now moved, I'll call this L sub 1. So let me relate all of these three variables. L naught is going to be the equilibrium position of the mass. U sub 1 is going to be the displacement of the mass from equilibrium. And L sub 1 is the final position of the mass. So I want to find an expression, which I'll call delta L, for the displacement of the mass from equilibrium. You already know what this is going to be, but again, I'm setting this up. I'm defining L naught U sub 1 and L sub 1, L naught, U sub 1 and L sub 1 for a reason, because I'm going to generalize this formalism. For our ultimate problem. Excuse me. And so what have we discovered? The change in L, the displacement of the mass from equilibrium, is just the final position minus its equilibrium or initial position. And so that's going to be L naught plus U1. Look at the diagram. L naught plus U1 is L sub 1. What I call L1 is really L sub 1. So I'll try to be a little bit more careful. And when I do this subtraction, I get that the displacement L is just U sub 1. Okay. So what are the forces on this system? I probably will go back here and just say, remind myself that L sub 1 is really L naught plus U sub 1. Well, I saw that was true from the diagram here. Okay, so I know my displacement of the system from equilibrium. What are the forces on this system? Well, I can write down Newton's second equation of motion. And in this particular case, what I'd like to do is go back to this problem and recognize that I'll pull the mass by a displacement U to the right and hold the mass. So F sub 1 plus F sub 2 would equal m times an acceleration. In this problem, there are no vertical forces, and the system, by holding the mass at rest, m times a is 0. Or really the 0 vector. A vector, scalar times a vector is a vector. So resolving this vector equation to its two components, remember, go back to the system. You've moved this to the right. Here's our mass, which we're going to represent by a point. It experiences two forces, F sub 1 and F sub 2. So resolving this vector equation to its scalar components, which is only one, I have minus F sub 1 plus F sub 2 equals 0. F sub 1 is the restoring force due to the spring. F sub 2 is the external force that you apply to hold the spring to hold the system at rest. Hooke's law tells you exactly what F sub 1 is. It's proportional to the displacement U sub 1, and that proportionality constant is just the spring constant. So my equation of motion is minus K U sub 1 plus F sub 2 equals 0, or F sub 2 is K times U sub 1. So what is the problem telling me here? It's telling me here that this force F sub 2, this is the force, excuse me, you must apply externally to keep the mass at rest. In other words, this is the force that you have to apply to fight the restoring force due to the spring. Okay? So again, here I've taken, in this particular case, case 2, I've taken my mass and spring, and I've moved the mass to the right by some distance for displacement U, and I hold it there. And in order to hold it there, I need to apply a force. This is exactly the force I need to apply. Now, third case I'm going to look at is, suppose you take this system and you let go of the mass. In other words, F sub 2, your external force, is now 0. So let's go back to case 2, look at the equation of motion for the system. Now, F sub 2 is 0. So in fact, this system is no longer at rest. F sub 1 is not 0, so there will be a non-zero acceleration. And now if I resolve this vector equation to its components, I only get that scalar equation. I know how to simplify this scalar equation. Hooke tells me how to do it. The restoring force F sub 1 is proportional to the displacement of the mass from its equilibrium position. And I finally have an equation which I can write. It's a second order linear differential equation, but it is the solution. Once you figure out how to solve this guy, it's the solution to the simple harmonic oscillator problem. Again, assuming no gravity, massless spring, one-dimensional motion. Okay. So it's probably useful to solve this equation to figure out what this system is doing. Now you can set up this experiment. You already know what this system is going to do. But the beautiful thing is the solution to this differential equation is going to tell you exactly what it does. So let's guess a solution for U sub 1. It's going to depend upon time. And let's say it's proportional to the sine of some dimensionless argument, which we'll call omega, and the product of omega and t. So the product of omega and t by dimensional analysis has to be dimensionless. And A has the same units as u sub 1, so it's some length. So if we use this guess solution, we can discover that the first derivative of u sub 1 with respect to time is just a omega cosine omega t. The second derivative of u sub 1 with respect to time is minus a omega squared sine omega t. But that's just simply minus omega squared times u sub 1. So if we look at this equation and we compare it to the solution or our formal differential equation we get when we solve the simple harmonic oscillator problem, then we discovered that the frequency squared, well, this term omega squared, I'll figure out what it is in a minute, is just equal to K over M. Okay, so what are these guys? A is what we will call an amplitude. It has length. T, of course, is time. Omega is what we'll define as an angular frequency, and therefore it will have units of inverse time. And my angular frequency omega is 2 pi times nu, where nu is what we will call our linear frequency. So nu has units of cycles per second, and 2 pi tells us the number of radians there are in a cycle. So my angular frequency has units of radians per second, and a cycle really is dimensionless. And now I can plot a picture of what this simple harmonic oscillator is actually doing. At time equals 0, so here is u of t, so here's my solution. I've guessed this solution, and it turns out that this would be is a great solution, provided that omega squared equals k over m. So this amplitude as a function of time is sinusoidal. So here I'm plotting displacement as a function of time. And what this is telling you is that you have the system at rest, you pull, let's highlight this in red, you pull the mass to the right by displacement. Let's say a maximum displacement here, and then you let go. And the mass just goes to the left. It goes through its equilibrium position at 0. It goes to the left of that equilibrium position. It reaches some maximum amplitude, A, which is the same as this guy. And then it starts heading back to the center, to the equilibrium position, and it just oscillates back and forth forever, since there's no friction in the problem. Hence, we have solved our simple harmonic oscillator problem. Okay. So now we're going to turn up the temperature a bit, make this a little bit more complicated, just to see what's going on. So here is my simple harmonic oscillator. Again, a massless spring of spring constant K attached to a mass. My system here is at rest, and there are no forces acting on the system. In this case, my system is my mass, M. There's no gravity here. I'm not pulling on this mass to the right. There's no external force. And there's no restoring force either. There's no restoring force because there's no displacement of the spring. The spring is at its equilibrium position. So according to Hooke, there is no restoring force. Now, I'm going to make this system a little bit more interesting. I'm going to take my mass, I'm going to attach it to one spring to the left, which I'm going to stretch, and then I'm attached to the right of the mass another spring. To make things simple, these two springs are identical, so they have identical spring constants. My mass will be at rest. So this dotted line indicates my equilibrium position. And I'm going to define L naught. Let's clean that up a bit. As I did before. She's going to be the distance from the wall to the mass, and the distance from the mass to the second wall. So what I've done in this diagram is I have stretched each spring to a new equilibrium position. Not the same equilibrium position as we had here, but I'll still call it, make my notation simple, L naught. And in this equilibrium condition, the system, namely the mass, is at rest. So let's analyze this thing. Again, I'll use my convention of the system or the mass as a dot. What forces act on the mass? Well, I could write down Newton's second equation of motion. So there's F sub 2, there's F sub 1. But again, this system is at rest. So there's no acceleration. So if we resolve this into its vector your components, in order for this system to be at rest, f sub 2 and f sub 1, their magnitudes are equivalent. So you may say, well, why go through the trouble of going through this example? Well, even though the system is at rest, if you cut, for example, the right spring, then there is no force due to that spring anymore. And your system would accelerate. If you just naturally come along and cut the spring, either one of them, that mass is going to move in a direction depending on which spring you cut. Okay. So let us take a 5-minute break here. Okay, so it may turn out that the previous part, there was a problem with the sound, so I will go through the process of simply repeating the previous section of the lecture before we had our last break. So what I wanted to do, or what I want to do next, is take this system where I have one mass coupled to two, connected to two springs. Spring constants are identical. Here my system is at rest, or it's in equilibrium. And I would like to alter it a bit. So here the equilibrium positions are L0 and L0 respectively. And what I'd like to do here is move my mass to the right. So again, this dotted line stands for the equilibrium position. So note a couple of things. The spring to the right is compressed. So there's going to be a force due to it because of Hooke's law. The spring to the left is stretched. So there's a force F sub 1, which is due to the displacement of the mass from equilibrium. But note that the displacement of the mass from equilibrium is greater in the stretched case than it is in the compressed case. So the magnitude of F sub 1 in this new case is going to be greater than the magnitude of F sub 2. So again, if I write my free body diagram, F sub 1 looks like that, F sub 2 looks like that. So let us release the mass. We've moved the mass to the right by some distance or displacement u sub 1. If you let it go, there's going to be an acceleration because there's going to be a net non-zero force on the system. Here's what it is. So I can resolve this into its vector components, only motion in the horizontal direction. And here is the equation of motion for the problem. The question is, what are these forces? So let's look at F sub 1. Again, it's a restoring force due to Hooke's law. So it's going to depend upon a spring constant and a displacement. So let's take the time to spell this out. And our diagram is highly instructive here. Namely, I will move the mass to the right by a displacement u sub 1. The distance from the wall to the original equilibrium position of the mass is L naught, and L sub 1 is just the sum of u sub 1 and L naught. So let's review these guys. L naught is the equilibrium position of the mass. U sub 1 is the displacement of the mass from equilibrium. L sub 1 is just L naught plus U sub 1, where L sub 1 is just the final position of the mass. So the displacement of the mass from its equilibrium position, delta L, is just the final position, L sub 1 minus L naught. That's going to be L naught plus U sub 1 minus L naught, and that's going to be U sub 1. So according to Hooke, F sub 1 is just K times U sub 1. All right, there's a second force because I have a second spring. Every time I have a force, every time I have a spring, I have a force. So what about F sub 2? So this is a restoring force due to the spring on the right-hand side of the mass. So again, let's put in our equilibrium position. Let's call the distance between where the mass is now been moved to, well, let's call this distance U sub 1, that's the displacement of the mass from equilibrium. And let's call the distance between that new position, and the wall L sub 2. So again, what are these guys? L naught is the equilibrium position of the mass. U sub 1 is the displacement of the mass from equilibrium, and L sub 2 is the final position minus the L sub 2 is just L naught minus U sub 1. I don't need parentheses there, sorry. Okay. That's just construction. That follows from the construction of this diagram. And so what is the total displacement? So this is a definition. So what's the displacement, delta L, of this mass from its equilibrium position? Well, it's just L sub 2 minus L naught, and that's L naught minus U sub 1 minus L naught, and that's minus U sub 1. So F sub 2, according to Hooke's law, is K times minus U sub 1. So what is our equation of motion? So our equation of motion is minus F sub 1 plus F sub 2 equals the acceleration of the mass times its mass. And F sub 2 we've calculated. Well, let's look at F sub 1 first. F sub 1 we've computed. So that's K U sub 1. F sub 2 is minus, or it's K, times minus U sub 1. So our equation of motion is the mass times the second time derivative of U sub 1 is minus 2K U sub 1. So note, there's a very neat check that you can do in this problem. If you add L sub 1 and L sub 2 together, so here's L sub 1, here's L sub 2. If you go to the trouble of adding those guys together, you get L naught plus U sub 1 plus L naught minus U sub 1, and that's going to be equal to 2 times the equilibrium position, which is a great check. That's exactly what it should be. Okay, so now we're ready to tackle the problem we set out to look at, namely that of the coupled harmonic oscillator. And I maintain that we've got all the machinery to solve this problem. So the coupled harmonic oscillator problem is going to be the next step in this process. Instead of having one mass, we'll have two masses. They'll be identical. And instead of having two springs, we'll have three springs. And they're all identical. Let's make our life easy. Let's remember what the equilibrium positions are for this system. this is a system that's at equilibrium. So I'm going to call the distance from the first wall to the first mass L0. The distance from between the two masses is L0. This is not drawn to scale, so my apologies. And the distance between the second mass and the second wall, L0. And so again, according to Feynman, you have to ask the question, what are the forces? Richard Feynman, celebrated physicist, always said that when you tackle problems like this, you have to pay attention to the forces. So I'm going to extract from this a free body diagram. The first mass has a force due to the spring on the left and a force due to the spring on the right. And the sum of those has to be 0 because the system is at rest. So this is the first mass. The second mass has a free body diagram also. And there will be a force due to the second spring, which we'll call F sub 3, of a force due to the third spring, which we'll call F sub 3, and there's a force due to the second spring, which we'll call F sub 2. So F sub 2 plus F sub 3 has to equal 0. Again, we're at rest. So note here a very interesting point. The first mass sees a force due to the first spring, sees a force due to the second spring. The second mass sees a force due to the third spring, but it sees a force due to the second spring, which is identical to the force that the first mass sees due to the second spring. There's one spring connecting these two masses. So F2 and F2 are the same vectors, they're just pointing in opposite directions. Again, a force uses its, or do it, a force depends upon a spring. So there are a couple of ways to do this problem. And since we've already started it, what are the forces? Then the next question is, what are the displacements? And then the last question is, what are the equations, plural, of motion? And it's equations, plural, of motion because you now have in this problem two masses. So you have an equation of motion for each mass. So it turns out we will tackle this problem accordingly. We'll actually deal with number 2 first, and then we'll look at the forces, and then we'll look at the equations of motion. Okay, so as advertised, you have to figure out what are the displacements. And I maintain that this is the most challenging part of the problem, but we have the sophisticated methodology or rules or battle plan to tackle this problem. So let's do so. So the first mass is going to be pulled from its equilibrium position, which is L0, by a distance u sub 1 with respect to the first wall. So there's going to be a distance L sub 1 between where that mass now resides in the wall. This is similar to what we did before. Okay, the second mass is going to be pulled from its equilibrium position by some distance u sub 2. It originally has a distance of L naught from the second wall. So this distance I'm going to call L sub 3. Finally, there's a second spring that connects the two masses. And the second spring is going to have a distance, which I'm going to call L sub 2. So L sub 2 is just the separation distance between these two masses. So L naught is an equilibrium position. It follows from the diagram. L sub 1 is what we saw, what was before. It's L naught plus U sub 1. Let me skip to L sub 3. That's just L naught, an equilibrium position, minus U sub 2. Now we have a new variable, L sub 2. What is it? This is just the distance between our two masses. Now, what is this guy? Well, originally the two masses were separated by the equilibrium distance, L naught. And then you pulled on the right-hand mass by some displacement U sub 2. So this became longer. But then you pulled on the left-hand mass by a distance U sub 1. So the net effect is to shorten this entire distance. Now, does this make sense? Yes. Because if in fact U sub 1 and U sub 2 are identical, then the separation distance between the two masses doesn't change. If you pull on the mass, if you pull on the spring, if you pull on the mass, second mass by a displacement U sub 2, and then you pull on the first mass by a displacement U sub 1, and those guys are the same, and the net effect is not to stretch the spring at all, okay? It's just, it falls to the limiting case that L sub 2 is just L naught. So let's check all of this to make sure it makes sense. If you add L sub 1 to L sub 2 to L sub 3, you get L naught plus U sub 1 plus L naught plus U sub 2 minus U sub 1 plus L naught minus U sub 2, and lo and behold, you get 3 times L naught, which makes perfect sense. The distance between the two walls should simply be 3 times L naught. So again, please check this. Please go over this argument. Make sure you understand all the variables and the constants. Make sure they make sense to you. See how they've been built on previous examples, okay? Because in a sense, this is all the work. You've done all the work. Okay, so now let's get equations of motion. There are two masses for the system. So let's just look at the first mass. Again, the free body diagram says it's a force to the left and a force to the right. So once you pull on that first mass to the right by displacement U1, you've set the whole system up so it starts to move. You can resolve this into its components. There's only one, there's only motion in the horizontal direction. And if you're going to make any progress now, you have to figure out what is the displacement due to F sub 1. In other words, Hooke's law. A force is due to a spring. So F sub 1, in this case, the displacement was initially L0. The final displacement of the mass, you move the mass so that it was a position L sub 1. So that's L0 plus U sub 1. So the displacement of the mass from its equilibrium position, the first mass, displacement of the first mass from its equilibrium position is going to be L sub 1 minus L0. And that's simply going to be L0 plus U sub 1 minus L0. And that's going to be U sub 1. Next, still with the first mass, what is the displacement due to F sub 2? Again, Hooke's law. Is in play. So the initial position, again, is L0. The final position of the mass due to the second spring is L sub 2. And that is L0 plus U sub 2 minus U sub 1. So I move that second mass, I move that first mass so that it sees a displacement from the second spring. The displacement from the second spring is in fact this. So the total displacement comes from taking the final position and subtracting from it the initial position. That's L0 plus U sub 2 minus U sub 1 minus L0, and that's U sub 2 minus U sub 1. So we can put all this together and we can write down an equation of motion for the first mass. It is mass times acceleration, and that's going to equal minus F sub 1 plus F sub 2. F sub 1, remember, is just simply U sub 1 times K times a minus sign. So the magnitude of F sub 1 is just K U sub 1. F sub 2 is just K times U sub 1, U sub 2 minus U sub 1. Again, check this. If the displacements U sub 2 and U sub 1 are identical, then the second mass, the second spring rather, doesn't have a displacement. So there's no force. And so all this does is reduce to the simple harmonic oscillator problem. And let's put that in red, that's important. Okay, 50% of the problem has been dealt with. I'm going to write this differently, actually. I'll rewrite it, combine terms, and I'll simplify the right-hand side of that equation. Okay, so that's a better better deal. Okay, so we've dealt with the equation of motion for the first mass. What about the equation of motion for the second mass? Well, the second mass, again, you ask the question, what are the forces? Well, the second mass sees a force due to the third spring and the second spring. And again, only horizontal motion. So resolve this in terms of its components. And here's the equation of motion for the second mass. So what is the displacement due to F sub 2? Well, we did this before. Remember, go back to our original picture. These two masses, actually, let's go back to this picture. These two masses are connected by the same spring. The spring is what causes the force, the restoring force. So F sub 2 and F sub 2 are the same for these two masses. It's just that they have different directions. So we can write down immediately the answer for the displacement due to F sub 2. What about, what is the displacement due to F sub 3? So we know the procedure. Here's the initial equilibrium distance, L naught. The final equilibrium distance, the final distance is L sub 3, but that's L naught minus U sub 2. So the displacement from equilibrium of the second mass for F sub 3 is just L sub 3 minus L naught. That's L naught minus U sub 2 minus L naught, and that's minus U sub 2. So what's the equation of motion for the second mass? The mass times the second derivative of U sub 2 with respect to time is minus F sub 2 plus F sub 3. And so this is minus F sub 2. There it is. At least that's the displacement part. So it's K times U sub 2 minus U sub 1. And F sub 3 is got to be K times minus U sub 2. So the equation of motion for the second mass is minus 2K U sub 2 plus K U sub 1. Okay, so the solutions, plural, to the coupled harmonic oscillator problem are as follows. The first mass has an equation of motion that looks like that. And the second mass has an equation of motion that looks like that. Similar, there's some symmetry, but they're not identical. Okay, so where is linear algebra going to come along and help you? So linear algebra is going to allow you to solve these two coupled equations. They're coupled because u sub 1, and u sub 2 appear in the first equation, u sub 2, and u sub 1 appear in the second equation. You can solve this problem exactly. Solve the coupled harmonic oscillator problem. And you can see physically what's going on. And I'll leave that to you as an exercise in problem set 11. I've given you some details, guideposts, but I'll leave that to you to do. So let's take a break here for about 5 minutes. Okay, so now we've gone through a second example of the eigenvalue problem. Let us ask a set of useful questions. That are going to get us to the point where we can start addressing the problem of diagonalizing matrices. So, all of this that we've done in this lecture and in lecture 10 is nice, and it's true, but what are some additional uses for eigenvalues and eigenvectors? Because after all, if the only useful application was the simple, if the only simple useful application were the compound harmonic oscillator problem, well, that's not a lot of motivation for studying eigenvalues and eigenvectors. And it's just going to lead us to the problem of diagonalizing matrices. So I want to go through some examples to motivate why all of this is useful. So suppose you have a matrix A that has 100,000 rows and 100,000 columns. That's a big matrix. And suppose you have a problem where you want to take that matrix and multiply it by a vector. Obviously, this vector has to have 100,000 rows and 1 column. So you can imagine all of the calculations you have to do to evaluate this creature. And this is going to be a very computationally expensive problem. Now, if in fact this matrix vector multiplication could be recast as an eigenvalue problem, then this is a much simpler problem to deal with, even if the vector has 100,000 rows and 1 column. Because all you have to do is multiply each one of those matrix elements by a single number, a scalar. And this problem is a much cheaper problem to study. So in fact, the eigenvalue problem, this is what it is. So let's give it its due and highlight it in red. This is the eigenvalue problem. On the left-hand side, you have a matrix multiplying a vector, which is computationally expensive. But if your problem solved could be recast as an eigenvalue problem, then all of that can be replaced by just taking a scalar and multiplying it by a vector to get a vector, and that's cheap. So that's one example of how matrix multiplication, or the eigenvalue problem, is something that's of interest in linear algebra. Let me go through a second example, and you'll have ample opportunity to explore this further in the problem set. Suppose you have a problem where you have a matrix A and you need to multiply it by itself 217 times. You need to raise it to the 217th power. Well, I know how to do that. I just have to keep multiplying this matrix by itself. And again, this is a very expensive problem. This is an expensive calculation to do. So we will show that this problem of just taking a matrix and multiplying it by itself 217 times is going to be equivalent to just taking the eigenvalue of that matrix and then raising that to the 217th power, which is going to be cheap. So this is something that, just whetting your appetite, this is something we will show. So eigenvalues are going to be useful. Okay, so we need to get to the task at hand now of diagonalizing matrices, what it is and why it's important. So I want to review some matrix multiplication. We've already discussed this in some detail. I just want to refresh our memories. Namely, if you have a matrix A, you can always recast it. Let's say it's a matrix that's 3 by 3, square matrix of order 3. You can always recast it so that its columns are the vectors b1, b2, b3. So that's a convenient way to write a vector in terms of column vectors. That's a convenient way to write a matrix A in terms of its column vectors. So let's have another vector, or a vector x, that's 3 by 2. What we discussed previously in previous lectures is that the matrix vector multiplication of A, the matrix A times the vector x, is the same thing as a linear combination of the column vectors of A. In fact, all that has to equal B. So in fact, you can write the matrix vector product as a linear combination of the column vectors of A, where the coefficients C1, C2, and C3 in that linear combination simply come from the values, the matrix elements of the vector X. Vectors are matrices. So there are two ways, at least two ways, to view matrix multiplication. Here's an example. Here's a matrix. Well, here's a matrix A. Here's a vector X. If I multiply these two things by using our convention of taking the row of the first matrix and multiplying by the column of the second matrix, I'll get C. And again, just second row, first column, D minus E, third row, first column, E minus D. I get a 3x1 matrix that looks like that. That result is equivalent to what you would get using method 2, which we just summarized above. Again, here's our original matrix A. Multiply it by the vector X. And what this is a linear combination of the column vectors of A, where the coefficients just come from the values of X. So if we add all these things together, namely, we use scalar multiplication. Here's a scalar, here's a vector, scalar, here's a vector, scalar, here's a vector, and then add those three results together. We should get C. We'll get D minus C here, and we'll get E minus D here, and we get the same result as we do up there. So that's helpful and useful. So what happens if we, well, now what happens when we revisit the task of multiplying two matrices together? In particular, let's take an example of A. It looks like that. And B, that we'll write in a general form. Both of these are square matrices of order 2. And they are certainly compatible for matrix multiplication. So let's ask, what is this? So if we use our definition from method 1 and just multiply a row times a column, it's really a dot product. You're taking the dot product of that row vector with this column vector. You'll get a 2x2 matrix. It looks like that. Let's clean that up a bit. A little bit too crowded. Let this thing breathe, have some air. So the 1-1 matrix element is A plus 2C. The 2-1 matrix element is 3A plus 4C. The 1-2 matrix element is B plus 2D. And the 2-2 matrix element is 3B plus 4D. Close this out. Well, I want to recast this. If I look at this first column, It's really 1, 2, 3, 4, that matrix times that matrix. And the second column is really 1, 2, 3, 4, that square matrix of order 2 times this 2x1 matrix. So what we're saying is that the matrix A times the matrix B is really the matrix A times this vector. And then, so you have two rows. As the first row, and the second row is A times this vector. And ultimately, you can write this as the product of A and B is just a matrix whose first row is A times B sub 1, sorry, whose first column is A times B sub 1, and whose second column is A times B sub 2, where B is a matrix that has two columns, B sub 1 and B sub 2. And this is a neat little thing to recognize. And we're going to use it subsequently. Okay, so let's return to our eigenvalue problem. Which says a matrix A acting on a vector V, if it's true that it gives you back the same vector times a scalar lambda, then that is the eigenvalue problem. Or in general, you can imagine having a problem where you have many eigenvectors, and each one gives you an eigenvalue. Excuse me. And this process goes on for n eigenvectors and eigenvalues. So linear algebra is the art of simplification, right? One of the things we want to do in linear algebra is make our life simple. So it's simplification. So can we recast these n equations into a single matrix equation? So that's the question. And the answer is yes, there's a way to do that. So it's worth the time to stop, sit back, and see how that's going to work. So we will do this as an example, and we'll do it only for two equations. With the idea that if you want to generalize this to three equations, 7, 39, or n, it's pretty straightforward to do. But again, as I've always said throughout the course, if you can see what happens for square matrices of order 2 or square matrices of order 3, it's easier to generalize that to square matrices of order n. So I'm going to define a vector S whose columns are the eigenvectors v sub 1 and v sub 2. So that means that that is a shorthand notation for a square matrix of order 2, has 4 matrix elements. There they are. Now, let's ask the question, what happens when you take the matrix A, and remember, the matrix A is a matrix whose columns are v sub 1 and v sub 2. Scratch that. Forget that. What I just said, that's not right. So A is just a matrix. So the question I want to ask is, what happens if I take the matrix A and multiply it by the matrix S? Well, as I said before, I know how to do this. This is just A acting on V sub 1, and it's A acting on V sub 2. So I get a new matrix where these two columns, C sub 1 and C sub 2, are defined accordingly. But according to the eigenvalue problem, when A acts on V sub 1, it gives you lambda sub 1 times V sub 1. And when A acts on V sub 2, it gives you lambda sub 2 times V sub 2. And again, to keep track of what's going on, S is a 2 by 2 matrix, and A is a 2 by 2 matrix. So can you write this out? I mean, this is convenient shorthand notation, but you always should be able to know what this means. The first column of the product of A with S is lambda sub 1 times V sub 1 times lambda sub 1 times V sub 2, 1. And then the second column is lambda sub 2 times V sub 1, 2. And it's lambda sub 2 times V sub 2, 2. Remember, the first subindex is a row index. Second one is a column index. Now, you will show in problem set (11) that in fact you can take this product and recast it as the product of two new matrices. S, that's what this guy is. Let's clean this up just a bit, right? And this matrix. So this is in fact S. It's the same thing as we did before. It's a matrix whose column vectors are just the eigenvectors of the problem. And here's a new matrix, D. And this matrix D is curious because it's a diagonal matrix. And furthermore, its diagonal elements are just the eigenvalues of the problem. Lambda sub 1 and lambda sub 2. So we put all this together, we have discovered that when you take A and act on this newly defined matrix S, which again is just a matrix whose column vectors are the eigenvectors for the problem, you get an interesting answer. You get back the matrix S times a diagonal matrix. So again, A is my original matrix. It has eigenvectors. You can build the eigenvectors. You can take the eigenvectors of A and build a new matrix S. So S is a matrix whose column vectors are the eigenvectors of A, and D is a matrix that's diagonal. But it's more than diagonal. The diagonal matrix elements are in fact the eigenvalues for the problem, lambda sub 1, lambda sub 2. So again, A acting on S gives you S back times D. It's not D acting on S. So that's something you'll check in problem set 11. And finally, if in fact the matrix S has an inverse, so that's a big if. That's not always true. This is a big assumption. But if this is true, that the inverse of S exists, then you can take the inverse of S and left multiply both sides of this equation, and you will find that the following is true, where what you have is your original matrix A as input. You can build from it a matrix S, assuming S has an inverse or it's invertible. Then you can perform the matrix multiplication prescribed on the right-hand side of this, and you'll get output, as output, a diagonal matrix. When you use this formula, you are in fact diagonalizing a matrix. So what I'd like to do to conclude today's lecture is go to an example with the caveat or warning, that I will give you lots of examples in problem set 11 and even 12 in diagonalizing matrices. So suppose I give you a matrix A, and one of the things that you should realize by now is that this matrix has to be a square matrix if you want to diagonalize it. So the task is give me a matrix A, which is square, diagonalize it. Okay, so what do you have to do? First thing you have to do is find the eigenvectors, or actually eigenvalues. The easiest thing to do is to find the eigenvalues. So let's find the eigenvalues of A. So we need to write down the secular equation or characteristic equation for this problem. That's easy. Here she is. You can multiply this out, this determinant out. You get lambda plus 2 times lambda plus 1. That equals 0. So lambda sub 1 has to be equal to minus 1. Lambda sub 2 has to be equal to minus 2. Second step of this matrix diagonalization procedure is for each eigenvalue, find the eigenvector. So again, everything in this course is cumulative, and these are skills that we've practiced before. So the first eigenvalue is lambda 1, that's minus 1. So I want to find a use of 1 that satisfies this equation, where u sub 1 is this vector. So I have the following matrix equation. That I need to write down and evaluate. This is going to give me minus 3x plus 2y equals minus x, and minus x will equal minus y. And you look at this, and at the end of the day, it's going to tell me the same thing, that x has to equal y. So the first eigenvector for lambda sub 1 is just this 2 by 1 matrix. And I'm going to let A be, this is the same standard fare that we've used before. A is going to be an arbitrary constant. Okay, so please check this. I'll give it to you, but check that in fact, this is true. Check that if you take A, which is this, and then you multiply it by u sub 1, that you get lambda sub 1, which is this, times the original vector, eigenvector back. Check that. Okay, next thing. How about the eigenvector associated with the eigenvalue lambda sub 2 is minus 2? Same story. I need to find an eigenvector u sub 2 that satisfies the following matrix equation. Let's write it out. And this should break down into two separate equations. Once I multiply those matrices out, minus 3x plus 2y equals minus 2x, and minus x should equal minus 2y. And so this is going to tell me, whoops, a little sloppy there, my apologies. So this is going to tell me that x equals 2y. And this is going to tell me the same thing. So u sub 2 is going to be 2b, b, those are the matrix elements, where b is an arbitrary constant. So what I have found is that u sub 1 is in fact this, and u sub 2 is in fact this. Remember, eigenvectors are not unique. They are known only up to an arbitrary constant. So to make life simple, I will set A and B both equal to 1. So there are my eigenvectors. So far, this is completely similar to the normal path that we've used for solving an eigenvalue problem. Now, here comes the new stuff, the good stuff. Now that I know the eigenvectors of A, I need to build this special matrix S. So S is just a matrix whose columns are the eigenvectors V sub 1 and V sub 2. So that's easy. There's S. Next thing, I need to find the inverse of S. So that's going to be easy for the case of a 2 by 2 matrix. This is just 1 over 1 minus 2 times this matrix, where those two matrix elements are flipped but that's okay because they're both the same. And I just put minus signs there. We've used this formula before, and this is just minus 1, 2. The 1, 1 matrix element is minus 1. 1, 2 matrix element is 2. 2, 1 matrix element is plus 1. And the 2, 2 matrix element is minus 1. So it is useful to, in fact, check this. So the inverse of S times S, let's see what this is. See, if we do a matrix multiplication correctly, that matrix element is 1, this is 0, that's 0, and this is 1. And that equals the identity matrix. And I ask you as an exercise to verify that this is true. Okay, so we're almost home. What do we know? We know A, we know S, we know the inverse S. So now we can diagonalize the matrix A. Matrix D, the diagonal matrix is SAS, where the inverse goes first. So the inverse of S is, in this example here, A in this example is just this matrix, and the S matrix is simply this. So what is this guy? All right, let's multiply the first two matrices together. So that's 3 minus 2 for the 1, 1 matrix element, minus 3 plus 1 for the 2, 1 matrix element. 1, 2 matrix element is going to be 2 minus 1 plus 0. And the 2, 2 matrix element is 2 times 1 plus 0. I have to multiply that by this. This is 1 minus 2 minus 2, 2. And let's see, this guy has to be what? Well, this has to be 1 minus 2. This is minus 2 plus 2. This is 2 minus 2. And this is minus 2 plus 2. And that's going to be equal minus 1, 0, 0 minus 2. And that is our diagonal matrix. And note the diagonal matrix elements are in fact the eigenvalues, lambda sub 1, which was minus 1, and lambda sub 2, which was minus 2. Okay. So this all checks. All right. So I will leave to you a problem set 11 more examples of matrix diagonalization. And how it has some useful applications, especially in terms of finding powers of matrices. So that's a very useful thing that matrix diagonalization is for. Okay, so this ends lecture 11. It's complete. We had 2 breaks, excuse me, at least 2 breaks, but the middle section, there was a technical problem with the sound, so I essentially repeated it. So this lecture is a little bit longer than a normal lecture, but it is intact and complete. Thanks very much. See you next week for lecture 12, where we will start talking about the least squares approximation, a beautiful way to take all these ideas of linear algebra that we've talked about throughout the course and bring them together for one useful example. Thank you.